we have to give our best for GATE exam as well as for all coming exams. Okay guys, so syllabus means in this session we will try to cover first of all semiconductor physics. Semiconductor physics, and this is a very important topic. Semiconductor physics means here we will try to cover what is the intrinsic and extrinsic semiconductor, that is the basic, about energy band diagram, conduction band, valence band, Fermi level, mass action law, Einstein equation, drift current, diffusion current, low level injection, pulse light method, dependency of mobility on electric field, drift velocity on electric field, and effect of temperature on mobility. These are all are the important topic. Law of neutrality we will discuss, continuity equation, okay, and then after that p-n junction. This is the first topic. Then second one is p-n junction. In p-n junction I will give you the formula about what built-in potential, that is the V naught. Then we will discuss transition capacitance, right, about electric field, what is the maximum electric field at the junction, and then junction potential. Then after that we will discuss diffusion capacitance, charge control description of the diode. Okay, this is about what p-n junction, and I will give you the formula of forward bias diode current, that is I, and you will get idea about reverse saturation current I naught. Okay, that is about the p-n junction. Now again in p-n junction we will discuss switching times, that is reverse recovery time and forward recovery time, storage time, transition time, that is called diode switching time. After that BJT, bipolar junction transistor. In this, input and output characteristics, input output characteristics, breakdown voltages, right, Ebers-Moll model, early effect, we will discuss all these things, and properties of common emitter, common collector and common base configuration. That is the case. Or you will get the idea about emitter injection efficiency, transport factor and so on. Then fourth one is MOSFET. Then MOS capacitor, you will get the idea about the MOS capacitor and all the formula related to MOS capacitor, all the important concept and formula for MOS capacitor. Right, remember that MOS capacitor is important topic. Every year there may be some conceptual question on this topic, MOSFET as well as MOS capacitor. Then spatial diode. Spatial diode. In spatial diodes you will get the idea about Zener mechanism and avalanche mechanism. And then what, p-n junction, solar cell and LED, right? So we will discuss the formula related to this diode. Quantum, you will get the formula of quantum efficiency and so on. BJT में confidence नहीं आ रहा है सागर रॉय, don't worry about that. एक आध दिन पूरा एक सेशन मेरा already available है on recorded lectures, और after Diwali we will try to arrange a regular session on that single topics like BJT, MOSFET, one day BJT, one day MOSFET and one day what other topics, so that you will get the idea about all the topics related to BJT. Don't worry about that. कोई हवा थोड़ी ने, they all are very easy topic. सबसे खतरनाक तो इंसान है, क्या है ना, उसको कौन डरा सकता है, क्यों सागर? ओके, अब देखिए जरा क्लासिफिकेशन ऑफ मेटल्स. फर्स्ट इन सेमीकंडक्टर, first point is what is the difference between the metal, semiconductor and what, insulator. Very first, very quick revision of all this topic. First of all, classification of metal, conductor and what, semiconductor. Conductivity, on the basis of conductivity, as you know, the conductivity of metal is very high. The conductivity of insulator is what, 0, almost 0 and very low. And what about the semiconductor? The conductivity is between that of metal and that of insulator. That is called semiconductor. Very simple definition. Now, most popularly used semiconductor is germanium and what, silicon. Germanium and what, silicon. Then these two are not used for preparation of LED or just right, fabrication of what? LED, that is light emitting diode. Here we are using gallium arsenide, germanium, silicon, then gallium arsenide. Okay, so these are the metal, semiconductor and what? Insulator. First, in insulator, semiconductor, metal, again classification on the basis of energy band diagram. First classification, we are having the two band, one is conduction band, one is called valence band. This is called lowest energy level of the conduction band, that is called highest energy level of the valence band. Then in case of insulator, the gap between EV and EC is more than 5 electron volt. More than 5 electron volt. That is called forbidden energy gap. That is an insulator. In case of metal, there is overlapping of right valence band and conduction band. Or in case of semiconductor, this is nearly equal to 1 electron volt, EC and EV. Now remember, this is 0.785 electron volt for germanium and 1.21 electron volt for silicon at 0 degree Kelvin. At 0 degree Kelvin. So in sometimes in a GATE exam, this time MSQ, multiple select questions. So they may ask, what is the EG at 0 degree Kelvin? 0.785 electron volt for germanium and 1.21 electron volt for silicon. So some student will say that, sir, 1.12 electron volt. Yes, that is at room temperature. What is the room temperature? 27 degree centigrade. That is known as 300 degree Kelvin. So what is the EG? It will become 1.12 electron volt for silicon and EG is 0.72 electron volt, nearly equal to that for germanium. Means when temperature increases, energy band gap decreases and EG is equal to EC minus EV. EG is equal to EC minus EV. So these are the values at 0 degree Kelvin. That is the first formula. Now next one. Here by agar aap, if you want the quick revision, then please stay here. It is around 1.5 hours or 2 hours, right? From 9 to 11, and you will get the complete summary of what EDC, that is electronic devices and circuit. Now, types of the semiconductor. Types of the semiconductor is what? Intrinsic semiconductor and what? Extrinsic semiconductor. Intrinsic means pure semiconductor, that is silicon and germanium. But the conductivity of silicon and germanium is very, very low, and that's why we are doping impurity, right? Those are called doped semiconductor or impure semiconductor or extrinsic semiconductor. So there are two types of impurity. One is called donor impurity, that is pentavalent, and one is called acceptor impurity, that is trivalent. Here n-type material, this is n-type semiconductor and this is what? p-type semiconductor. In intrinsic semiconductor, remember I am giving you the important formula. J is equal to what? Sigma E. J is equal to sigma E, means J is proportional to E, that is the Ohm's law, and sigma is the conductivity. Sigma is given by NQ mu N plus PQ mu P for semiconductor. NQ mu N plus PQ mu P. N is the concentration of electron, P is the concentration of hole, Q is the charge, 1.6 into 10 raised to power minus 19 coulomb. That is the value of Q. In some book it is represented by E, no problem. Mu N is the mobility of electron and mu P is the mobility of hole. And mu N is greater than mu P. Always remember, mobility of electron is greater than mobility of holes. That is the general formula for conductivity. Then this, for intrinsic semiconductor, the conductivity will become NIQ mu N plus niq mu p, because n is equal to p is equal to ni. Intrinsic carrier concentration, therefore niq mu n plus mu p. That is the conductivity. So in case of intrinsic semiconductor, the conductivity is because of electron as well as because of holes. But the contribution of electron is greater than what? Contribution of hole in this conductivity. Reason, the concentration is same, Np is equal to Ni, but mobility is greater. Mobility of electron is greater than mobility of holes. That's why the contribution of electron is more. Very simple reason. When we are saying that it is p-type, then the conductivity is mainly due to holes, that is pq mu p, p-type. When we are saying that it is a n-type, then the conductivity is mainly due to electron, nq mu n. So some students are confused with the n. Remember, it is not number, it is the concentration. Concentration means per unit volume. So what is the unit of n? Per centimeter cube. Unit of p per centimeter cube. What is the number of electrons per unit volume, or what is the number of holes per unit volume? That is called concentration. Okay. Then that is the structure of what? Intrinsic semiconductor. Covalent bonding, sharing of the electrons. Covalent bonding and sharing of electrons. Okay guys, remember that here it is a 4 in outermost orbit, there are 4 electrons, that is a tetravalent. Now it will share electron with the neighboring atoms, and this is the bond, covalent bond. Next, in p-type semiconductor, that silicon is replaced by what? Boron. Boron is a trivalent material, that is the outermost orbit, we have the 3 electrons, right? Now because of that, one hole is created. That is what this, that's why it is called p-type material. Okay. Next one, this is a boron, is a trivalent material. Then in n-type material, this is arsenic, pentavalent. It will replace the silicon, that is the silicon, that is the outermost electron is electron in outermost orbit is 4. Here in outermost orbit electrons are 5, right? It has one extra electrons, it will donate the electron, and that's why it is converted into n-type, right? So in a trivalent it will accept one electron, and that's why that atom is called acceptor atom. Here it will donate one electron, that's why it is called donor ion, donor atom, okay, or donor impurity. Now this is an important table here. What are the important values? First of all, electronic charge 1.6 into 10 raised to power minus 19 coulomb. Mass of the electron 9.1 into 10 raised to power minus 31 kg. So normally we are not using that value, that is Q by M ratio. So sometimes it will save your time for calculation. Q by M ratio 1.759 into 10 raised to power 11. Planck's constant, this is very important one, 6.626 into 10 raised to power minus 34 joule second. Unit is joule second. Voice break हो रहा है फिर से. Everyone please inform me that it is okay. Voice not clear again. What is the problem? Give me 1 minute. Now it is fine. Tell me. Now everything is fine. It is not okay. Again your video is not visible. Give me 1 minute. Wait for 1 minute. I think now everything is fine. Okay. Just I have started. We have to discuss number of formula. Video is blur. Now please inform me that everything is fine. Okay, give me comments. All good. Thank you. Now, so these are the important values of electronic charge, electronic mass, ratio of Q by M, that is Q by M, Planck's constant. Another one is Boltzmann constant. Normally it is represented by K or K bar. 1.381 into 10 raised to power minus 23 joule per Kelvin. Or here is another Boltzmann constant. That is in what? Electron volt. 8.620 into 10 raised to power minus 5 electron volt. So some students are confused with the electron volt. Remember that it is a unit of energy, that is electron volt. It is nothing but this E is replaced by what? Q. So 1.6 into 10 raised to power minus 19 joule. Right? 1.6 into 10 raised to power minus 19 joule. So that is the value of 1 electron volt. So what is the meaning of 1 joule? 1 joule is equal to 1 divided by 1.6 into 10 raised to power minus 19, and that will give you the number of electron volt. Number of electron volt. So similarly in a Boltzmann constant, 1.381 into 10 raised to power minus 23, that is joule per Kelvin. So what is the 1 joule is equivalent to this much electron volt. So 1.38 into 10 raised to power minus 23 divided by 1.6 into 10 raised to power minus 19, that is converted into electron volt per degree Kelvin. Divide this value and you will get this one, last one. 8.620 into 10 raised to power minus 5 electron volt per degree Kelvin. So no need to mug up. No need to mug up the concept. Simple, remember that. So 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joule, and that is the value in electron volt per degree Kelvin. It is in joule per degree Kelvin. Now epsilon naught. Normally we are using the epsilon naught, that is 8.854 into 10 raised to power minus 12 farad per meter. And in number of cases we are not using farad per meter. We are using what? 8.854 into 10 raised to power minus 14 farad per centimeter. So normally we are using farad per centimeter. So remember, you have to change 10 raised to power minus 14 farad per centimeter. That is for free space. And then I will share the another values, epsilon r and epsilon naught for germanium and silicon and so on. Next one, the mobility and electric field. So that will be available to you in the form of PDF, don't worry, but you have to attend the class so that you will get the idea how to use this formula. Okay, how to use all these formula. No, Ravi. Normally we are not using farad per meter. In electronic devices, normally we are using farad per centimeter. Why farad per centimeter? Because all the doping concentration are given in what? Na is given in what? Na is given in per centimeter cube. Nd given in per centimeter cube. Psi is normally given in centimeter. That's why epsilon naught we are using 8.854 into 10 raised to power minus 14 farad per centimeter. So be careful. Mobility centimeter. What is the unit of the mobility? Centimeter square per volt second. Again here we are using the centimeter. So in a 90% case, we are using what? Centimeter square or centimeter. Okay, so sometimes students are highly confused. For example, 1 micrometer, that is 10 to the power minus 6 meter. But what is the 1 micrometer is equal to 10 to the power minus 4 centimeter. Right? Then please try to understand all this, because quickly we have to use all this. One in Armstrong. What is this? Meter. Very small thing but very important thing. Is equal to what? 10 to the power minus 8 centimeter, and so on. These are the units of the length. Okay. Next one. Mobility and electric field. As you know, drift velocity is proportional to what? E. And drift velocity is equal to what? Mu n, mu into E. Where the constant of proportionality is what? Mu. That is called mobility. Okay. But when we are again voice break, बीच बीच में हो रहा है. अभी बताओ साउंड क्वालिटी अभी ठीक है क्या? गिव मी 1 मिनट यार, इसको थोड़ा सा ठीक कर लिया जाए. क्या प्रॉब्लम है? Now tell me that is everything is fine now. Yes, please. Sir, all good. Please refresh your system then. If you find any difficulty, then please refresh your system. Okay, all good. Okay, then in a semiconductor, as field intensity increases, drift, first of all, mu d. But what will happen? That initially the mobility is independent of E. That is independent of E up to E is equal to what? 10 to the power 3 volt per centimeter. After that, mobility is proportional to 1 by root E. For E, between 10 to the power 3 is less than E is less than 10 to the power 4 volt per centimeter. And after that, mu is proportional to 1 by E for E greater than 10 to the power 4 volt per centimeter. These are the values. So if the mu is not independent, and that's why in this range, Vd increases linearly with electric field. In this range, Vd increases sublinearly. Why? Since mu is proportional to 1 by root E, that's why now the Vd is proportional to root E. Now here the mu is proportional to 1 by E, that's why Vd is independent of E. Or here the Vd will become constant. That is called saturated drift velocity. Saturated drift velocity. It is the highest velocity, drift velocity. Saturated drift velocity or highest velocity. So that is the case. So this is the diagram. So up to this range, mobility is constant independent of the electric field. After that, 1 by root E, it is proportional to 1 by root E. And now it is proportional to 1 by E. It decreases, again decreases. This is the increases linearly, then sublinearly, and after that it will become constant. And that is called saturated drift velocity. This is the saturated drift velocity. So that is the curve, mobility and electric field. Right. Again, watch this. We are calculating the electric field. What is the unit? Volt per centimeter. So because the size of the conductor, this is in the range of what? Centimeter. It is not in the range of meter. The size of the conductor, it is in the range of what? Centimeter. Cross-sectional area and so on. Or in case of MOSFET, the size in what? In the range what? Micrometer. In case of MOSFET. That is in size, it is in centimeter, and that's why. Now, effect of temperature and doping. Watch this diagram carefully. In electronic devices and circuit, there will be question on this. Now we have approximately one range here, around 100 degree Kelvin. Before this, right, it is a log scale. right? When here we are moving here, temperature increases. Watch this diagram. When I am moving from left to right, first of all, the mobility increases. Mobility increases with the temperature. And after that, it will reach to a maximum value. And after that, it will decreases. It will decrease. The actual curve is like this. This is the curve. Okay. It will reach to maximum at this point. After that, it will start decreasing. So there are two effects. One is called impurity scattering and other one is called lattice scattering. So at a low temperature, impurity scattering dominates, or at high temperature, lattice scattering dominates. Okay. So because of lattice scattering, the mobility will decreases when we are increasing the temperature. We are increasing the temperature, mobility will decrease. Remember that. In this case, when we are decreasing the temperature, the mobility will decrease. So here, decreasing the temperature, mobility decreases. That is called impurity scattering, and it is nearly below what? T is equal to 100 degree Kelvin. And the temperature is less than or equal to 100 degree Kelvin. Approximate value. Or when the temperature is greater than 100 degree Kelvin, temperature increases, mobility decreases. Lattice scattering. So normally we are dealing with the devices at which temperature? 300 degree Kelvin, that is at room temperature. So we are saying that when temperature increases, normally mobility decreases. Right? Mobility decreases. So that is the case. Okay. Sir, directly proportional. Okay. What is the directly proportional, my dear? Here. First of all, the drift velocity is directly proportional to what? E. And mobility is independent. So in second case, if the mobility depend upon 1 by root E, or it depends upon E, so what is this? Vd is proportional to what? Root E. That is the change. So here it is increases linearly, here it is increases sublinearly. And third one, Vd is proportional to, mu is proportional to 1 by E, and into E. So E cancel. It is constant. It is independent of what? It is independent of electric field. I think that is clear. So mobility constant, decreases, then again decreases with increase in E. Increases linearly, sublinearly, and it will become constant. Saturated drift velocity. Mu d, Vd is equal to mu E means what? Yes, that is the formula. Vd is equal to, I am giving the proportionality that Vd is equal to mu E. Okay. That is the formula. Right? Now, this is about the temperature. Then watch this diagram carefully. Again at room temperature, 300 degree Kelvin, right? Suppose we are saying that impurity scattering will not affect the system at 300 degree Kelvin because it is effective at low temperature. But no. Right? So first of all, you have to get the result, my dear. In a gate exam, you have to score the rank, right? You have to got right. So give the gate, get the good rank, get the good score, and then we can fill the form for what? PSUs. Okay, Hariharan. Sometimes they will conduct interview for you, or sometime written test. Okay, watch this. This is the mobility of electron. Always remember the mobility of electron is greater than mobility of holes. So this is the mobility. This graphs, all the graphs are very, very important. In electronic devices, always 1 or 2 question from graphs. So this is the graph. This is the 1000. This is the 500. And it is at room temperature. That is the 300 degree Kelvin. 300 degree Kelvin. What is the doping? Only 10 to the power 14. when we are increasing the doping in this direction, 10 to the power 14, 10 to the power 15, 10 to the power 16, 17, 18 or 19, then the mobility decreases from 1000, more than 1000, around 1200, it decreases up to what, 100. That is the change in mobility, 10 times. Or this is the from 500, it is reduced up to what, 50, again 10 times. So that is the change in the mobility of electron as well as change in the mobility of holes when we are increasing the impurity concentration. That is Nd increases, mobility of electron decreases. Right? Remember, this is a very, very important formula. Na increases, mu p increases, mu p decreases. Exactly at 300 degree Kelvin. So sometimes we are thinking that when we are increasing the concentration, then definitely the conductivity will increase. No doubt. Conductivity depends upon two things, sigma and q mu n. So it depends upon the concentration. So when we are increasing the Nd, definitely the concentration will increase, conductivity will increase. But when we are increasing the Nd, what is the side effect? Mobility will decrease. When the mobility will decrease, conductivity will decrease. So ultimately we have to check what about the product. If the product increases, then conductivity increases. If the product decreases, then conductivity what? Decreases. And that is the difference between what? Thermistor and sensistor. That is the difference between thermistor and sensistor. In a thermistor, the doping is normal, means it is a lightly doped semiconductor. Or in sensistor, highly doped semiconductor. And that's why when we are saying that what about the temperature and what is the effect of that, then we have to consider the product of mobility and concentration. Okay, so that is the I will explain you the thermistor and sensistor. So that is the case. Remember, this graph is very important. Already one question in GATE exam, previous year question paper, you can watch on this diagram. Okay. Now, law of mass action. It is a written content, but here watch, that is simple. Np is equal to what? Ni square, where N is the concentration of electron, P is the concentration of free holes. Ni square, that is called intrinsic carrier concentration, is given by A naught T cube e raised to power minus Eg0 by kT. Eg0 is the gap energy exactly at 0 degree Kelvin. Energy band gap at 0 degree Kelvin. K is the Boltzmann constant, T is the temperature. If Eg0 is in electron volt, then you have to put the Boltzmann constant in electron volt per degree Kelvin. That is the value. Now, in N type, according to mass action law, always remember, we are saying Nd. So what is the concentration of electron? Minority carrier concentration, that is given by Ni square by N or Ni square by Nd. That is the formula. Very easy. In P type, what is the concentration of hole? Na. What is the concentration of electron? Ni square by P, that is Ni square by Na, according to mass action law. Normally we are using this formula. Or in P type, majority carrier is hole and minority carrier is electron. Now, law of neutrality means positive charge, concentration of the positive charge is equal to what? Concentration of negative charge. An intrinsic or extrinsic semiconductor is electrically neutral, whether it is P type or N type or intrinsic type, all are electrically neutral. And that's why the concentration of positive charge is equal to concentration of negative charge. Nd, it is called donor ion. It is a positive charge, that is represented by this one. Hole, that is represented by this symbol. It is again a positive charge. Na, that is the acceptor ion, trivalent, because of trivalent atom, that is the negative charge, and electron is represented by dot, that is again a negative charge. So concentration of positive charge is equal to concentration of negative charge. That is the value. Okay. So that is these are the important formula related to this one. Now Fermi-Dirac function, or that is the Fermi distribution function. Okay, that is important formula. This is give the probability of finding an electron at a particular energy level, that is the Fe, 1 upon 1 plus E minus EF by kT. Here E is the energy level, EF is the Fermi energy level, K is the Boltzmann constant, T is the temperature. This is the important formula. Fe represents the probability of electron to occupy a certain energy level. E is the energy of the state. With the help of this formula, we can find the probability of finding an electron at this particular energy of the state. EF is the Fermi energy level or characteristics energy. And if for any crystal exactly at E is equal to EF, what is the probability? If suppose I am putting the E is equal to EF, then it will become e raised to power 0, that is nothing but 1 by 2. So for any temperature, it is independent of the temperature. For the crystal E is equal to EF, then Fe is 0.5 for any value of temperature. Any value of temperature. Now, it is also called as Fermi-Dirac probability function or Fermi energy density function. It specifies the fraction of all state at energy E occupied under thermal equilibrium condition. So there may be MSQ on it. MSQ, multiple select question. At T equal to 0 degree Kelvin, E minus EF is less than 0. E is less than EF. So what will be the probability? You can check the probability when I am putting, for example, exactly at 0 degree Kelvin. Watch this formula. When I am putting 0 degree Kelvin and if the E is less than EF, then it will become e raised to power minus infinite and probability will be 1. You can write like this. E is less than EF, that's why we can write EF minus E divided by KT. And what is the T? 0 degree Kelvin. And that's why e raised to power minus infinite, this is 0 and the probability is 1. For T 0 degree Kelvin, E minus EF, if it is less than 0, for E less than EF, the probability is exactly equal to what? 1 according to the formula. Similarly, for E greater than EF, at 0 degree Kelvin, you can find the probability E minus EF by 0. This will become 1 upon 1 plus e raised to power infinite, and that is nothing but 0. That is the graph. 0 probability, 1. This is the graph exactly at 0 degree Kelvin. When we are increasing the temperature, the probability of finding an electron at this point decreases and probability of finding electron at this portion increases. That is the above energy level. So this is the graph with the temperature T1 and that is the graph with the temperature T2. That is the T2 is greater than T1. So this is a graph related to what? Fermi-Dirac distribution function. Okay. So they may ask some questions on this, but now concentration of electron. Concentration. This last year one question on this formula. Remember that they will give you the value of Nc and so on. So N concentration of electron is given by Nc e raised to power minus Ec minus Ef by Kt. That is the formula. In exponential term, N Nc, that is called density of state in conduction band, e raised to power minus Ec minus Ef, where Ef is the Fermi energy level, upon Kt. Upon Kt. That is the concentration of electron. Then this is similarly the concentration of hole is given by Nv e raised to power minus Ef minus EV by KT. EF minus EV by KT, where density of state in valence band NB. Okay, so they will provide you the data, what is the value of NV and what is the value of NC, or they will give you the relation between NV and NC. So you can use this formula and you can find the concentration of hole or concentration of electron, right? Now with the help of these two formula, first one and second one, right, we can get the what is the difference between the Fermi level and what conduction band, what is the difference between the Fermi level and what valence band, that is EF and EV or EF and EC, we can find with the help of this formula. Now finally, in intrinsic semiconductor, Fermi level EF is given by, that is the formula. How we can find this? Then there was one question on this last year. This is the EV, EC, this is the middle level, EV by 2, EC, right? So for intrinsic semiconductor, EC plus EV by 2 minus KT by 2 log of NC by NV. You have to remember that formula, NC by NV. So exactly when NC and NV are not same, then Fermi level is not just in the middle of what? Forbidden gap energy level. This is called EG, forbidden energy gap. It is not in the middle, exactly not in the middle. That is the formula. You have to subtract KT by 2 log of NC by NV and you will get exact location of Fermi level for intrinsic semiconductor. But normally in numerical it is NC or NV is given. When the effective mass of electron and holes are equal, the log of 1 will become 0. In that case, EF is equal to EC plus EV by 2. EC plus EV by 2. Remember this formula, this is important one. It is a Formula 1 series and that's why, my dear, quick revision of all the formula, right? So please revise all this formula and you can make also short notes of all this. Then next one, for N-type semiconductor. N is nearly equal to ND. We are giving donor impurity. Then EV, EC, intrinsic Fermi level. Now that is the Fermi level EF. Intrinsic Fermi level, we can say this is the EC, EV, sorry. EFI, conduction band, valence band. Then the gap between EF and EFI, this gap is given by KT log of ND by NI. KT log of ND by NI. So normally we are having question on that. What is the gap EF minus EFI? That is given by KT log of ND by NI. Okay. And then second one, for P type, P is equal to NA. This is the intrinsic Fermi level. And that is the exact Fermi level here. This is EFP for p type, EV, EFI, and that is EC, conduction band, valence band, and this gap is given by KT log of Na by Ni. Na by Ni. Ni is the intrinsic carrier concentration. Okay. So hello Karan, how are you? After long time. भाई देखो जरा एक बार आप लोग दीपावली, इस दीपावली में सभी ध्यान दीजिएगा कि आपको अगेन कंसंट्रेट करना है, एक रिजोल्यूशन लीजिएगा, 2 दिन आराम से घूम फिर कर आइए, राइट, और उसके बाद बिल्कुल भिड़ जाइए, और साथ में इस बार आपको अपना सब कुछ लगा देना है, रिजल्ट की परवाह नहीं करना है, राइट। तो डोंट वरी अबाउट द रिजल्ट, बस आप डायरेक्शन में पढ़ाई करते रहिए और सिस्टमैटिक ढंग से नोट्स बनाते रहिए। याद रखिएगा बहुत ज्यादा पढ़ना मतलब हार्ड वर्क करना जरूरी नहीं है। अगर गेट में आप टॉप करना चाह रहे तो आपको स्मार्टली वर्क करना पड़ेगा, कौन कौन से टॉपिक, कौन से फॉर्मूला, कौन से क्या चीजें इंपॉर्टेंट है और एक्चुअली एग्जाम हॉल में कैसे अप्लाई करना है, ये ज्यादा इंपॉर्टेंट है। ओके, तो वैसे तो पढ़ने के लिए बहुत कुछ है। अ वेरी गुड इवनिंग इला, हाउ आर यू? देन दिस इज द पी टाइप, दिस इज द Na, तो दैट इज द KT log of Na by Ni, that is the gap. Now current, we are having two types of current. Normally we are dealing with the drift and in what? Diffusion. Drift means under the influence of electric field, and diffusion current basically because of concentration gradient. So what is the concentration gradient here? So that is we are having normal we are expressing the current in what? In the form of current density. So what is the current density? J is equal to I by A. J is equal to what? I by A. Again, what is the unit? Ampere per centimeter square. Ampere per centimeter square. That is called current density. So what is the drift and what is the diffusion? So that is the drift current density. J is equal to sigma E, that is the drift current. For metal it is given by NQ mu n into E. That NQ is called volume charge density. Remember that is the volume charge density. Rho, this is the rho, and the unit is coulomb per centimeter cube or per meter cube, rho, and mu n into E is called drift velocity. And that's why the J is represented by rho Vd. Rho Vd. Sometimes direct question on this formula, rho Vd. Okay, that is called drift current density. But in case of semiconductor, we have electron as well as holes. Then simply you can represent, already I have given J is equal to sigma E. And what is the sigma? NQ mu n into E. That is the J. Plus PQ mu P into E. That is for semiconductor. Okay. Yes, Kumar. Karan. हाँ, यू आर इन सेकेंड ईयर, तो मैं कैसे तैयारी कर सकता हूँ, ये भी बड़ा प्रश्न है कि व्हाट इज द राइट टाइम टू स्टार्ट फॉर गेट 2020 या 24 और 25। बस आप मतलब जो भी आपके सेमेस्टर में सब्जेक्ट है, फॉर एग्जांपल इफ द नेटवर्क और डिजिटल और कंट्रोल, राइट, इलेक्ट्रॉनिक डिवाइसेस, तो दीज आर द सब्जेक्ट इन योर सेमेस्टर, एज वेल एज मैथ्स 1, मैथ्स 2, मैथ्स 3 और एप्टीट्यूड। तो go with all these subject, right, for semester exam as well as for competitive exams, and don't worry about the other subject. Okay, simply focus on semester exam और इन सब्जेक्ट को तैयार करो कॉम्पिटिटिव एग्जाम्स के लिए, जो जो भी कॉमन सब्जेक्ट है आपके सेमेस्टर में। और अभी मेरे ख्याल से सेकेंड ईयर में ऑलरेडी स्टार्ट हो जाता है सर्किट थ्योरी, नेटवर्क और बहुत सारे सब्जेक्ट ऐसे होंगे जो सिलेबस में कॉमन है। तो पहले गेट का सिलेबस, ईएस का सिलेबस प्रॉपरली देख लीजिए एंड देन उसके हिसाब से आप अपनी तैयारी स्टार्ट कर दीजिए। तो 2 साल में बहुत अच्छे से, जो भी आपका फर्स्ट ईयर में है स्टूडेंट या सेकंड ईयर में है या थर्ड ईयर में, तो थर्ड ईयर वाला स्टूडेंट तो एलिजिबल है, लेकिन सेकंड ईयर स्टूडेंट को लगता है कि कई बार ये बहुत जल्दी प्रिपरेशन तो नहीं होगी, तो आप एडवांस मत जाइए। जो भी आपके सेमेस्टर और गेट में कॉमन सब्जेक्ट है उनको पहले तैयार करो। सेमेस्टर में भी अच्छा परफॉर्म करोगे, कॉलेज वाले भी खुश रहेंगे, प्रोफेसर भी आपसे खुश रहेंगे, राइट। और प्रैक्टिकल भी कीजिए और साथ में प्रीवियस ईयर क्वेश्चन भी बनाते रहिए, ताकि आपको आइडिया लग जाएगा कैसे क्वेश्चंस आते हैं। ओके। और एक बहुत ही इंपॉर्टेंट चीज है मैथ एंड एप्टीट्यूड। मैथ और एप्टी मिला के यार 28 मार्क्स का आ जाता है, तो कोशिश कीजिए कि ये 28 मार्क्स तो फिक्स कर लो, ये तो सेकेंड ईयर तक फिक्स हो जाता है मैथ्स एंड एप्टी, उसके बाद गो फॉर रिमेनिंग मार्क्स। ओके, so that is the simple strategy. Okay, these are the formula. Next one, this is about the drift current. Already I have given you the formula. Now diffusion current. So what is this? Is a very important concept here, diffusion current. Remember that. Number of questions on this diagram and so on, so please watch this. If suppose this is the whole concentration, here the concentration is very high, here the concentration is low, then what will happen? This is in x direction, this is positive x direction, and that is the y-axis. In our y-axis we are representing the concentration, on x-axis we are representing the distance. So here it is a higher concentration, here it is a lower concentration. There is a concentration gradient and the hole will move from higher concentration to lower concentration. When hole are moving from higher concentration to lower concentration, definitely current will be in the same direction. But when the current is in the same direction, why we are putting the minus sign here? Why we are putting minus sign here? Because J is equal to I by A, and it is given minus Q dP by dx. Minus Q. That is in formula we are using minus. So some students are saying that it is a minus, it is the charge is negative and so on. No, no, no. The value of Q is simple, 1.6 into 10 raised to power minus 19 coulomb. So when we are putting the minus sign means, watch this diagram. Right. Let linear decrease in the concentration. Concentration at this point is 1000 and the concentration at this point become 100. That the distance at this point, that is 0, or the distance at this point is 10 centimeter. Tell me what is the slope of this line? What is the slope of this line? So we are saying that slope will become, slope is negative. So 100 minus 1000, that is called concentration gradient. P2 minus P1 upon X2 minus X1. 100 minus 1000 divided by 10 minus 0, it will become minus 900 divided by 10 minus 90. So we are getting the dP by dx negative. When the dP by dx is negative, this Q is the positive value, dP is the diffusion constant or diffusion coefficient. When we are putting this value, you will get the positive value here. You are going to get the positive value. And what is the meaning of the positive value? That meaning is that current is in positive x direction. Yes, it is a higher concentration, it is a lower concentration. Definitely the hole will move in x direction and current will be in the same direction. Move from higher concentration to lower concentration and current will be in the same direction. So we are putting negative sign so that numerical value will be positive. Means current is in positive x direction. If we are getting the negative answer, means current is in negative x direction. So that is the meaning of this formula. Okay, I think now it is clear. This is an important one. Number of questions on this. Similarly for electron, we are using J is equal to q dn by dx. Okay, so no doubt it is a positive, but it depends upon the concentration dn by dx. Okay, that is the formula for electron and hole. Diffusion current density. So here this is for electron, q or e, same thing. Right, next one. Einstein relation. dn by mu n is equal to dp by mu p is equal to Vt, that is Vt is the volt equivalent of temperature, that is given by kT by q. Already I have given you the value of k, q and t. You will find the Vt is equal to 0.0259 volt at 300 degree Kelvin. It is nearly equal to T by 11,600 volt, or we are using Vt is equal to nearly equal to 25 millivolt at 298 degree Kelvin or 25 degrees centigrade. Normally we are using these two values, Vt 26 millivolt at or 25 millivolt. In GATE exam normally 25 millivolt is given, that is at 25 degrees centigrade, and that is the Einstein equation. Now pulse light method. Pulse light method, from this we are simply giving the light at this point. New hole electron pair is generated. At this point generation rate and recombination rate will become equal, and that's why after that it will saturate. Now the light is turned off. Now the concentration will start decreasing. With the help of pulse light method we can find, right, we can find what? Mean lifetime, that is tau p or tau n. In this exponentially decreasing function, what is the equation here? After that, this is the t equal to 0. At this point light is off. We are moving with the time. With the time the concentration of hole is given by thermally generated charge carrier, that is it is a n-type bar, plus excess hole concentration exactly at t equal to 0, e raised to power minus t by tau p, where tau p is called mean lifetime, right? So with the help of pulse light method we can find the mean lifetime. That is important one, and remember this equation. Remember this equation. Then it is function of time. This is the pulse light method, hole concentration, and these are the formula, e raised to power minus t by tau p. Second one is called injected minority charge carriers. Right, in injected, number of questions on this diagram. Electronics and telecommunication, what is the doubt? Sir, every time I have doubt between the electron volt and volt in case of Einstein relation, please clear. Okay, what is that? What is your doubt? My dear, dp by mu n is equal to dp by mu p. It is a Vt. So here we are using Vt in volt only, right? Remember that. dn, diffusion constant. Mu n, mobility, is equal to what? Vt. Remember, what is the unit of the mobility? Centimeter square per volt second. When it is multiplied with the volt, so what is the unit of the dn? Diffusion constant is mu n into Vt. So volt to volt cancel, and the unit is centimeter square per second. That is the unit of diffusion constant or diffusion coefficient. Why you are using the electron volt here? Electronics and telecommunication engineer, that is clear. So why you are using? No doubt, in an energy gap, sometimes it is confusion when we are saying that this is the Fermi level, or when we are calculating the gap. No doubt, there is some confusion by we are using kT by Q or kT. Very simple. When it is multiplied with the Q, it is converted into electron volt. We are not putting the value of Q. If suppose we are putting the value of Q 1.6 into 10 raised to power minus 19, then it is converted into what? Joule. Right? For example, if simply I am multiplying with what? Vt is equal to Q or something else. That V is multiplied with the Q. So that unit is converted into what? Electron volt. Because we are not putting the value of Q. Once you are going to put the value of Q, that is 1.6 into 10 raised to power minus 19 coulomb, then it is converted into what? Joule. Okay, so we will solve some numericals on that. Or formula, injected minority carrier. We are giving the radiation at this point, and this is a n-type bar, that is the distance in x. New hole electron pair is generated here. Now the hole will move from higher concentration to lower concentration. There will be the recombination, and in an open circuit bar, the current will be zero. Because of this radiation, there is a development of internal electric field. That is the value. You are saying that Vt, that Kt, where Vt is in volt and Kt is in electron volt. Okay, you are saying that. 1 minute, I am going to explain you. No problem. 1 minute, give me 1 minute. First of all, watch this. Simply you are saying that, sir, I am Vt. Oh, that is the confusion. Okay. You can put it in what? If suppose you are putting in electron volt, then no need to put the value of Q here. Q will cancel out and you will get the directly T by 11,600. First of all, go through the table, use the value of K in electron volt per degree Kelvin. Kelvin is cancel out. This E and that Q is cancel out and you will get the answer. That is 11,600. Okay. Second thing. Second. If suppose you are going to put the K in what? Joule per degree Kelvin. My dear, put the K in Joule per degree Kelvin, but you have to put the value of the Q also. So you have to put, if suppose you are putting the K Joule per degree Kelvin, it should be divided by what? 1.6 into 10 raised to power minus 19 into T. And then K in Joule per degree Kelvin. Then you will get the same answer, that is T by 11,600 in both the cases. If you are putting in terms of electron volt, then simply this E or Q is cancelled out by this Q. No need to write the value of Q and you will get the answer. Okay. Now I think it is clear. That is the low level injection and that is the diagram, my dear. This is called excess hole concentration. This is called minority charge carrier here. And this is important formula. P naught plus P dash 0, this is the excess hole concentration, e raised to power minus x by LP, where LP is called diffusion length. Diffusion length for holes. So this is the diagram. So in number of cases we have to use this diagram to find the diffusion current. Okay, that is the value. So remember that it is with respect to what? Distance. With respect to distance. Now Hall effect. With the Hall effect, we can find whether the semiconductor is p-type or n-type, right? With the Hall effect, here we are giving the magnetic field, that is B. In x direction, there is a current I, and because of this B and I, there will be the force in the downward direction, that is F. And with the help of this, we can find whether it is n-type or p-type. We can also get the value of N, that is the concentration, or P. We can also find the mobility of majority charge carrier, that is mu N or mu P. If it is P type, then we can find P, then we can find mu P. If it is N type, then we can find the concentration as well as mu N, that is the majority charge carrier. Okay. Remember that it is not used for minority charge carrier. It is used for what? Majority charge carrier. We can find the mobility of majority charge carrier, Hall effect. Then What are the application? That is, they may ask MSQ. Hall effect multiplier first. Second, right, magnetic field meter. Magnetic field meter. These are the application of what? Hall effect. Hall effect multiplier. Second one is magnetic field meter. We can design with the help of Hall effect. Now there are two types of semiconductor. One is called direct band gap semiconductor and another one is called indirect band gap semiconductor. So direct band gap semiconductor means gallium arsenide, and we are using it for LED, light emitting diode, because when electron jump from conduction band to valence band, it will recombine with the hole, then it will give the energy in the form of light. Or in case of indirect band gap, when the electron switch, it will give the energy in the form of heat. For example, germanium and what? Silicon. That's why germanium and silicon are not used to fabricate LED, that is light emitting diode. Now these are the property of what? Silicon and germanium. These are the property of silicon and germanium. First of all, which property are important for competitive exams? First, atomic number, okay, 32 and 14, tetravalent. Atomic weight not required, density is not required, dielectric constant, yes, 16, 12, sometimes it is used 11.7 for silicon. Atom per centimeter square, per centimeter cube, that is normally given in the question. Eg naught, yes, it is required, 0.785, 1.21. Then at room temperature, Eg naught become 0.72 or 1.1 electron volt. Intrinsic carrier concentration, sometimes it is given in the question, sometimes it is not given in the question. Then you have to use the standard value. 2.5 into 10 raised to power 13 for germanium and 1.5 into 10 raised to power 10 for silicon. That is, these are the important values. And again, intrinsic resistivity, that is normally given in the question. For germanium, resistivity is very small. For silicon, intrinsic resistivity is very, very high. Mobility, always remember, this is for germanium 3800, 1300. Mobility of electron is greater than what? Mobility of holes. Watch this. What is the mobility of holes? 1800. What was the mobility of electron? 3800 for germanium. This is the mu p. Mu n is greater than mu p. Similarly, what is the mobility of silicon electron? Mobility of electron in case of silicon? 1300. And what is this? 500 for holes. That is for silicon and that is for germanium. So you can find the ratio of that between 2 and 3. That mu n by mu p is between 2 and 3. Then diffusion constant. Okay. And that is normally it is given in the question. Power handling capability of germanium is low. Power handling capacity of silicon is high. That is a very simple formula. PDF will be available to you. So that is the important properties and so on. Okay. Next, this is the continuity equation. It is based on law of conservation of charge. Based on law of conservation of charge. Okay. So remember, that is the formula. The rate of change of concentration is given by 1 by Q. That is the current density upon dx. That is the rate of change of the current density with respect to distance, plus generation rate minus recombination rate. You have to use this formula. Continuity equation. Second, similarly for whole continuity equation, dp by dt is equal to minus 1 by q djp by dx plus generation rate minus recombination rate, where G and R represent the carrier generation and recombination rates, These equations require models for mobility and recombinations along with models of contact and boundaries. That is a very, very important formula from the continuity equation. Remember that last year in 2022, one question on continuity equation. Already I have given the solution. Please go through that. This is a very, very important question on continuity equation in 2022. Okay. Okay then. How to apply this formula? You will get the idea. Now we will enter into what? This is all about the semiconductor physics. Now we will enter into what? P-N junction. P-N junction. P-type, N-type. Simple. We are taking what? Single semiconductor bar, and one side we are giving Na doping, other side we are giving Nd doping, and that is converted into P-N junction. When here we are giving the Na doping, here we are giving the Nd doping. It is a single semiconductor bar. कोई फेविकॉल का जोड़ नहीं है ना, याद रखिएगा. It will accept one electron and create holes. It will donate one electron and become positive ion. Right? So this is the case. This is the Na, that is what P type, and this is what Nd type. The concentration of hole in this region is very, very high. The concentration of electron in this region is very, very high. There is a metallurgical boundary between P and N type. There is no physical boundary. There is a metallurgical boundary. Right. Now, here only that is number of things are not mentioned in the syllabus. Okay, they are simply giving what? Semiconductor physics, intrinsic semiconductor and extrinsic semiconductor. Okay, Nachiket. So for last 2 years, there were last years there was some question on Hall effect. No doubt it is not mentioned, but in a semiconductor physics, if suppose we are going to get one question, then it will be in syllabus. Okay, that is the way. There. So negative, 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 and that is the positive Na. This is a large hole concentration. Then initially in an open circuit bar, what will happen? The concentration of hole is very high. The concentration of a hole in this region is very low. Concentration of electron in this region is very high. The concentration of electron in this region is very low. Therefore, initially the hole will move in this direction, from higher concentration to lower concentration. Electron will move in this direction, from higher concentration to lower concentration, and because of this the current will be in the same direction, Ip and In, and that is called diffusion current. But in an open circuit bar there will be no current, right? And to stop this diffusion, built-in potential will develop, and that built-in potential is given by VBI. This is the built-in potential because of this uncovered immobile charge carriers. Right? In a space charge region, we are developing immobile charge carriers. Right? There is a recombination of hole and electron. Then, in that creation of the depletion region, in depletion region only immobile charge carrier exists. Because of this, electric field develop. The direction of the electric field is this, from this point to this point, and there is a built-in potential. So what is the formula for the built-in potential? V0 or VBI, that is given by Vt log of Na Nd by Ni square. This is the built-in potential. Okay, so remember that formula. Second, this is the space charge region. Here we are having the negative charge, that is negative ions. Here we are having the positive ions, and this is called space charge region. The direction of electric field is from positive to negative. it will force the hole in this direction, in opposite direction, and diffusion will, because of diffusion, hole will move from left to right, and because of that electric field, hole will move, try to move from right to left. Similarly, electric field force on the electron in this direction, left to right, and because of diffusion, the force will be from right to left. They will cancel each other. And in an open circuit bar, what will be the current? 0. That is given in the direction, and so on. Now, what is the formula and diffusion capacitance and transition capacitance? Now I will give the formula. First of all, I is equal to I naught e raised to power V by eta Vt minus 1. That is the formula for forward bias diode. This is the voltage across the diode V. Eta ideality factor 1 for germanium, 2 for silicon for rated current. If in any question high current is mentioned, then it is 1 for both germanium and silicon. If high current is mentioned, it is for rated current. Then I naught, that is called reverse saturation current, and it is given by N. That is the formula for reverse saturation current, I naught. It doubles for every 10 degree rise in temperature, and that's why at any temperature it is given by 2 to the power T1 minus T by 10. That is the formula for reverse saturation current. Right? Vt already we have idea about that, Kt by Q. That is T by 11,600 volt. T by 11,600 volt. This is exponentially increasing function. So remember some questions on that, on reverse saturation current. That is the formula. First of all, we have to find the reverse saturation current by using this formula. Here dp is the diffusion constant or diffusion coefficient for hole, dn is the diffusion coefficient or diffusion constant for electron, Lp is called diffusion length, Ln it is called diffusion length for electron, this is for hole. And what is the relation? Lp is equal to root over dp tau p. Tau p is the mean lifetime of hole. Ln is equal to root over dn tau n. Dn tau n, that is the formula. When we are saying that what is the P n naught, this is the minority charge carrier, that is given by Ni square by Nd. And what is the Np naught, that is given by Ni square by Na. Ni square by Na. These are the important formula. Okay. If you have any doubt, then you can ask. It is a quick revision of all the formula. That is about the diode. Now, second important thing, when the diode is reverse biased, there is a transition capacitance. There is what? Transition capacitance. Depletion layer increases, depletion layer increases. This side, this is called Wn. This side, it is called Wp. Diffuser length on P side, diffuser length on N side. And because of this, when we are increasing the reverse voltage, depletion layer increases, and therefore there is a change in charge. When there is a change in charge, always there is capacitance. Change in charge because of change in voltage. And this type of capacitance is called depletion capacitance, transition capacitance, or space charge capacitance. So what are the important formula related to that? First, the transition capacitance is given by epsilon naught epsilon r A by W, where W is the depletion width. Epsilon r is relative permittivity, that is nothing but 11.7, or sometimes it is given 12 for silicon. A is the area of cross section, epsilon naught already I have given the value in the table. and W is the depletion width. Then second thing, Vj, junction potential, that is given by V0 plus Vr. V0 is the built-in potential, Vr is the applied voltage in the reverse direction, that is given by Qn by 2 epsilon s. Again, this is the epsilon s, means epsilon naught epsilon r, permittivity of the semiconductor, into W square, where n, this is given by 1 by n is equal to 1 by Na plus 1 by Nd, or n is given by Na Nd upon Na plus Nd. Na Nd upon Na plus Nd. Now that is the formula. Built-in potential means Vt log of Na Nd by Ni square. In number of questions we have to calculate these values. This is for step graded junction. This is for step graded junction. Okay, then normally this W, from this we can say the W, that is the depletion width, is proportional to root over Vj, and C is proportional to 1 by W, therefore C is proportional to 1 by root over Vj. Therefore, if we have to find the capacitance, then always remember CT2 by CT1 is given by root over V0 plus VR1 upon V0 plus VR2, because it is inversely proportional, and that's why you will get this ratio. That's why you will get this ratio. With the help of this, directly you can solve question. Use this formula. A number of questions on transition capacitance. Okay, then this is the important one. Now, in sometimes there is some confusion in Na. Always remember, if Na is very greater than Nd, then N is nearly equal to what? Nd. Or if Nd is very greater than Na, then N is nearly equal to what? Na. Always remember smaller one. Smaller one. For example, Na is very greater than Nd, then Nd is negligible, this Na cancel, and what is the N? Nearly equal to what? Nd. So directly you can use this formula. Okay. So already I have given the IV characteristics, that is the eta, and germanium for low current, that is for rated current, and that is the temperature. All the PDF will be available to you on my Telegram channel. Now I am sharing my Telegram channel link. 1 minute. Yes, that is Electronics by Sanjay Rathi. So I will upload the PDF of analog 1, analog 2, part 1 and part 2. Already I have shared the password in second class, and then I will upload the EDC. Okay, and at the last I will give you the password for this PDF. That will be the password protected. Okay, so that is the formula. This is about the diode. Now important one, that is another one, is what? Diffusion capacitance. Remember that when the diode is forward bias, then there is a diffusion capacitance. It is an incremental capacitance defined as the rate of change of injected charge with the voltage, called the diffusion or storage capacitance. So what is the important formula for diffusion capacitance? That is tau G. Tau is the mean lifetime and G is the incremental conductance, that is given by tau I by eta Vt, where I is the current through the diode in forward bias, eta ideality factor, and Vt is volt equivalent of temperature, tau G. tau I by eta Vt. Remember that formula. Okay. Or in a previous formula, always remember, if the diode is forward biased, then this junction potential, if suppose the diode is forward biased, then the junction potential will become V0 minus Vf. That is, when we are applying forward voltage, that is the Vf. Then built-in potential, it will reduce the potential barrier. So therefore, V0 minus Vf means capacitance will increase. When we are increasing the VR, V0 plus VR, it is inversely proportional. That's why capacitance will decrease. And when we are making it forward biased, so what about the capacitance? Will increase, and that's why we are getting this type of curve. Right. This is the applied voltage. It is in forward bias, it is in reverse bias. When we are increasing in reverse bias, capacitor will decrease. Exactly, there is no biasing, then this is the value of the capacitance. When we are increasing the voltage in forward bias, because of this, the capacitance will increase. Here it is called diffusion capacitance. Here it is called transition capacitance. When the diode is reverse bias, transition capacitance. When the diode is forward bias, it is called diffusion capacitance. Okay, so that is important formula. Right. This one, Varactor diode. Varactor diode means that CT is proportional to what? 1 by root over Vj, or that is CT is proportional to Vj raised to power minus 1 by 2. In a reverse bias, Vj is given by V0 plus Vr. When we are changing the value of voltage, the value of the capacitance will change, and that's why it is called volta cap or variable capacitor or Varactor diode. That is the equivalent circuit for the Varactor diode. Remember, there may be one numerical on that. The symbol for this is a variable capacitor, that is an equivalent. Because it is reverse bias, the resistance is very high, that is in the range of mega ohm, and that is the transition capacitance. Rs, it is the resistance of packing material, or just when we are connecting the lead, for example anode and cathode. So that is the, because of this connection, it has resistance that is represented by Rs. This is called series resistance. It is a very small value. So what is the typical value of this resistance? That is written here, 1 mega ohm, because the diode is reverse bias. What is the value of the capacitance? 20 picofarad. And what is the value of series resistance? Only 8.5 ohm. Right. So these are the physical parameters. So sometimes to solve the numericals on that, we have to represent the Varactor diode by its equivalent circuit. So remember that it is connected in parallel. Then that is the case. Sometimes we have to find what? Resonance frequency. This type of questions. Integration of what? EDC and network. Now my dear friend, BJT. That is all about the PN junction BJT. Basic structure of BJT, as you know, this is called emitter, this is called base, thinnest part, and that is called collector. Emitter, the doping of the emitter is highest, area of the collector is highest, thinnest part is what? Emitter, base. Since the base is the thinnest part, the resistance is highest, because what is the rho? R, rho L by A. Area is low, that's why resistance is high. Now this is called emitter base junction, that is called collector base junction. Symbol for NPN transistor, this one, and that is the symbol for PNP transistor. P type emitter, N type base, P type collector. Right? Emitter act as source, collector act as sink. That is the diagram. Now, mode of operation: cutoff, active, saturation and reverse active. In analog, already I have discussed what are the application and what are the properties of common emitter, common collector and common base. Why I have explained that in analog? Because some topics are common in analog and what in EDC, right? Without getting a basic idea about the properties, we can't solve the question. So already I have given, but you can go through this. What about the emitter based junction, collector based junction? What are the properties and applications? So in cutoff and saturation, it acts as a switch. Normal active mode we are using for amplification, or reverse active mode is rarely used for low amplification. No doubt we are using it, but it is used for low amplification. For example, we are using the that reverse active mode in TTL, that is the transistor logic. Yes, that is the use. Now, NPN transistor in active region. NPN transistor in active region, there are number of current source and so on, that is given in this diagram. That is the diagram from one standard textbook, that is what Niemann. Okay, so which formula are important on the basis of this diagram? That is emitter injection efficiency factor. This is important for electronics student. Emitter injection efficiency factor, that is 1 minute. Oh, there is some printing mistake. That is the emitter injection efficiency factor. This is not the case. This is the base transport factor. Okay, no doubt, misprint. Give me 1 minute. Yes. Okay. Emitter injection efficiency factor is gamma, and this is base transport factor is alpha T. Now, JNC upon JNE, that is the current density of that is the collector current density upon emitter current density. This is because of emitter current because of the electron. This is the emitter current because of the electron upon emitter current because of the electron, emitter current because of the holes. This is called emitter injection efficiency, and then this is called recombination factor. So that is the total emitter current density JNE plus JP. This is the JNE plus JP plus recombination in emitter base junction. So out of these three formula, these two are very important one. Base transport factor and emitter injection efficiency factor, right? So please remember these two formula. We have to use this to solve some important numericals on that. Base transport factor, and this is injection efficiency. Now, early effect, that is very important phenomena in case of what BJT, that is also known as base width. What is round tube? What is the base transport factor, you are asking? Okay, try to understand. Right, watch this diagram. There is a very small depletion region here in base emitter junction, and there is a depletion layer in a collector depletion region. This junction is forward bias. This is NPN transistor, and this junction is reverse bias. Okay. Now, when we are making it forward bias, large number of hole will move from, electron will move from this point to this point. That is called diffusion, and they will constitute emitter current density JNE. At the same time, large number of holes will move from P side, from base side to N side, and they will constitute emitter current. The direction, it is in opposite direction, and they will constitute JPE. and finally this is the emitter current I. Or when we want to find the density, it should be divided by A. That is because of electron and that is because of hole. Now the electron will move, some will recombine and the remaining will reach here and they will constitute a collector current density that is given by JNC. So my dear, tell me, all the electron will reach to the collector or some will recombine in the base? So some electron will recombine in the base, and that's why the JNC is always less than JNE, and that is called transportation factor. This point is clear? Okay. That is base transport factor. Second one, what is the emitter injection efficiency? Emitter current is because of electron as well as holes, but electron will contribute in collector current. The current due to hole will not contribute, and that's why what is the injection efficiency? JNE. It will contribute in collector current, but what is the total emitter current? JP, because of holes plus because of electron, and that is called emitter injection efficiency. Okay guys, now it is clear. Now again we are having the more current here. So what about the some current? Some current will because of recombination in this region. When we are considering the recombination, the emitter base junction, then we have to give the formula for this one. That is called recombination factor here. JR. Recombination JNE plus JPE upon JNE plus JR plus JPE. So it complete, it will constitute a emitter current, which out of these JNE and JPE is usable. JNE and JPE, only JNE is usable, and out of JNE only JNC will reach toward collector region. That is the ratio. And then overall alpha, we can find the overall alpha. Normally it is given in the question. That is the product of these three. Right? Alpha T into what? Gamma into what? Delta. Product of these three. I think now round tube it is clear. Okay. Right. Then early effect. Early effect means simply because of this early effect, when this collector junction is more and more reverse biased with the help of this VCB, when we are increasing the VCB, the collector junction is more and more reverse biased, the depletion width increases, and the increase in the depletion width is called early effect or base width modulation. Right? So base that is JR is nothing but recombination in what? Emitter base junction. Recombination in emitter base junction, that is given here. And they will constitute an extra current, right? JR. New hole electron pair will generated here, then again recombination, and they will constitute they will contribute in the emitter current. Actually we are measuring the emitter current, but emitter current is divided into three parts. One is JNC, JPE, JNE, and what? JR. Right? That is the recombination in this junction. So normally that is not given in the question. They will give you the idea about the base transport factor or emitter injection efficiency. If it is given, then we can consider it. Right. Then early effect. So when we are increasing the VCB, depletion layer increases, recombination will decreases, because when the depletion layer increases in the base, depletion layer means there is no mobile charge carrier exist. If no mobile charge carrier exists, means simply recombination will reduce. Then more electron will reach to collector junction. When more electron will reach to collector junction, definitely the collector current will increase. Collector current will increase. Remember, in case of NPN transistor, collector current inside, emitter current outside, base current inside. That is the direction of the collector current, base current, and emitter current. So what is the early effect? Simply, when VCB increases, collector junction more reverse bias, depletion width increases, effective base width where recombination occur decreases, recombination decreases, and because of this alpha increases. When alpha increases, IC increases, but base current decreases. This is the early effect, right? Now, so what is the effect of this? Remember that because of the early effect, we are having elevated curve like this. In common emitter characteristics, we are having elevated curve. And so, this is the value. Okay. That is the different values of IB. That is the VC and this is the IC. That is elevated. When we are extending, all will meet at a point. This is called early voltage. This is minus VA. VA is called early voltage. With the help of this, we can find the R naught. This is given by VA upon ICQ. Right. And then, normally we are having the formula for IC is equal to I naught e raised to power VBE upon VT in case of transistor. Remember that I naught upon e raised to power VB upon VT. That is the formula for collector current when the emitter junction is forward bias. But when we are considering the early effect, it will become IC is equal to I naught e raised to power VB upon VT into 1 plus VC upon VA. That is, we have to multiply it. And this is the with considering the early effect, it is the without early effect. These two are the important formula in electronic devices and circuit. They will give you the value of VB, reverse saturation current, VT. You have to find the IC. Then with the help of this IC, you can find the, or if the early effect is given, then you have to multiply it with what? 1 plus VC by VA. Then we can find the formula for IC. Second, in active region, IC is equal to 1 plus beta times of ICU. No problem. Beta IB plus 1 plus beta times of ICU. It is also applicable. IC is equal to alpha I plus ICU. Alpha I plus ICU. These are the two formulas. Normally we are saying that that is for common emitter and that is for what? Common base. But remember, we can use both equation depend on each other. Because what is alpha? Alpha is equal to beta upon 1 plus beta. And what is the beta? Alpha upon 1 minus alpha. Right? And that is the value. Beta IB 1 plus beta ICO and alpha I plus ICO. This is the formula. Both are valid for active region. Beta is called large signal current gain for common emitter. Alpha is called large signal current gain for common base. Okay, any doubt? Please ask me. Up to this point, any doubt? Okay. There is another important current, that is when base is open. Base is open means when the base current is 0. There is a current from collector to emitter when the base is open. That current is given by ICEO. ICEO, that is the current from collector to emitter when base is open. So when we are making the base open, means IB will become 0. That is nothing but 1 plus beta times of ICO. So this is nothing but ICEO. So from this formula, you can say ICEO is nothing but 1 plus beta times of what? ICO. 1 plus beta times of ICO. There is another current when emitter current is 0. Emitter current is 0 means emitter is open. Then there is a current from collector to base, and that current is this one. This is called ICBO. Current from collector to base when emitter is open. Current from collector to base when emitter is open. So from second formula, if suppose I am making the IE is equal to 0, so what is this ICBO? So what is the ICBO is equal to ICO? When I am making the IB is equal to 0, ICO. ICO is equal to, this is 0 plus what? 1 plus beta times of ICO. So that is the difference. So ICBO is nothing but ICO. Reverse saturation current when the collector junction is reverse bias. So it means directly you can say that ICEO is greater than what? ICBO. 1 plus beta times of that. So sometimes we are using that formula. And there is another relation between the ICBO and ICO. This is for ideal transistor. But for practical transistor, ICBO is slightly greater than ICO. ICBO is slightly greater than ICO because of avalanche multiplication. In a reverse bias junction, always there is a avalanche multiplication, and because of that reverse saturation current increases. So in a theory we are not considering. It is a theoretical reverse saturation current. It is a practical reverse saturation current. And second one is surface leakage current. Always there is some current through the surface. So ICBO is slightly greater than ICO. So practically we can arrange ICEO is very greater than ICBO, or ICBO is slightly greater than what? ICO. Or ideally these two are equal. Number of questions on this formula. Okay. Okay then. This is about the transistor. Now we have to arrange one more session on that. Okay. In next session, already the properties and the values, that is already I have given in what? Analog. So in next session we will start with what? Field effect transistor, that is FET. Field effect transistor, that is FET or MOSFET, metal oxide semiconductor field effect transistor. Here we will discuss what? All the important formula, and then after that MOS capacitor. All the different modes, accumulation mode, depletion mode, right? And inversion mode. Junction capacitance. We will discuss what are the important formula for all the capacitance and so on. So that is about this topic. And now, my dear friends, already we have discussed the number of properties and so on. The password is properties for PPT. Okay, properties. So all the properties are all in small letters. I will upload the PDF on my Telegram channel, that is Electronics by Sanjay Rathi. Okay. So thank you for attending the session. You are on BYJU'S exam prep. Please like the session, subscribe our channel and share the link of this session. Thank you very much, and again happy Diwali. Thank you.